All right, this is Algebra 1's Chapter 1 exam review. So we're going to cover everything here that was in Chapter 1 that could show up on your first semester exam. You can use these sheets on the exam like notes. So make sure that you are putting lots of good work down so you can look back, see how to do these, not just have an answer, and that will help you tremendously on the exam. All right, so we're going to kind of squeeze all this work in. There's not a lot of room, but we don't want a lot of extra paper floating around when we're trying to take our exam. So we're going to try and fit everything onto this paper. So we'll see how we do. So we're going to simplify each expression using order of operations. So that's what we're doing here. Remember, order of operations was PEMDAS. Probably seems like a long time ago now. So we've got parentheses, exponents, multiply, divide, add, and subtract. All right, I'm going to move this one over a little bit, move it up. In the process, I'm going to start simplifying some things. We multiply and divide before we subtract. Okay, and some people think that you multiply first and then you divide. This is 1. This is 2. Multiply and divide is 3. Add and subtract is 4. So you multiply and divide at the same time, whichever comes first. So in this case, the first thing we see here is division. So even though there's multiplication and division, since it's to the left, I'm going to divide first. So 36 divided by 3 is 12. And I'm just going to bring everything else over. So all I've done is this. So I still have times 4 and minus negative 2. So I'm down to subtraction and multiplication. Multiplication will come first. So this is 48 minus negative 2. You can use your calculator. Remember that minus and negative is like adding. So this is 48 plus 2. And my final answer here is 50. All right, sliding over here. So I look for parentheses first, and these parentheses represent multiplication. These parentheses were just containing that negative. So we're not talking about those types of parentheses. We're talking about when there's actually an operation inside of it, like we see the addition here. So we're going to want to take care of that. I'm going to simplify this right under it, and then I'll bring it up. So 10 minus 70 minus 5. And now 2 plus 1 up here in the exponent becomes a 3. Okay, so I've done the parentheses part. That's what I'm doing first. Plus 4 times 30. Now I'll bring it up over here. In that process, I am going to do the next step, which is exponents. So 5 to the third. Be careful, it's not 5 times 3. 5 to the third is 125, which came from 5 times 5 times 5. 5 times itself 3 times gets you that answer. So as I move this up, I'm going to change that to 125. So it's 10 minus 70 minus 125 plus 4 times 30. All right, when I look across this, all I see is subtraction and addition, except for right here, we've got some multiplication. So that's going to be the next step. I'm going to do that next. Over here, I did this. So everything comes down, except I'm going to do this multiplication. And so that's going to be 120. So just like we talked about over here, adding and subtracting happens at the same time. You don't add first and then subtract. So you do it from left to right. So since that's all I have left, I'm just going to take care of this, and then this. And the last thing I'm going to do is that, just left to right. So 10 minus 70 is negative 60. Left to right, negative 60 minus 125 will get you negative 185. And now I'm going to go ahead and add that, and I get negative 65. There we go. All right. Next little section here, we're going to evaluate each expression when x equals 10. So we're just plugging in for the x, and we're going to put 10 in there. And then we're still following order of operations after that. So if I slide this over, 10 is going to go in for x. Here's how I would like you to write it. This is 5 times 10 squared. You could also put it in parentheses if you wanted to. All right, so I have substituted in. Next, I need to follow my order of operations. So parentheses, I don't have any exponents, I do. So I'm going to leave the 5 and the times alone. 10 squared is 10 times 10, that's 100. And now all I have is multiplication. And my answer is 500. Okay, second one looks similar, right? 5x squared, and I still have a 5x and a squared, but I've now got parentheses around that, which will change things. Okay, so I'm still plugging in 10. So here's what this is going to look like. Inside parentheses, when you have a coefficient attached to a variable, that's multiplication. So this is 5 times x, which we're going to substitute in 10. And then the exponent is on the outside. So parentheses is first. I have an operation inside parentheses. So before I do any of these exponents, I actually have to do the multiplication. Now, because multiplying comes before exponents, because it doesn't, but parentheses does. So first thing I'm going to do is multiply inside parentheses. So 5 times 10 is 50. The squared now is attached to the 50. And you plug that in your calculator, 50 to the second power, or that's 50 times 50 is 2,500. All right. Moving into chapter 1.2. So we looked at patterns here. So we're going to give an instance for this pattern, and it says remember to show your work and simplify. So we're basically just going to pick whatever number we want for x and plug it in and show that this pattern actually works. So if you look at your answer key, the instance that's shown there is 5. So I'm going to choose something different so you have two good examples to look at. If you'd like to add the x equals 5 from the answer key pattern onto your notes, might not be a bad idea to have two examples. Okay, but I'm going to do x equals 2. So I'm rewriting all of this, including the equal sign, and substituting in my choice of 2 for x. And you can pick whatever number that you want that makes this true. So on the left side, it's going to be 4 times 2. And then I have 1, 2, 3, 4 x's. So 2 plus 2 plus 2 plus 2. And then you just simplify both sides and show that it does come out equal. 4 times 2 is 8. And 2 plus 2 plus 2 plus 2 is also 8. All right, so that's an instance. An instance is an example that shows it works. Now they want you to give a counterexample for this one. So a counterexample proves that this is not always true. It's an example where this is not true. So I should get a different number on each side. So let's say you picked 0. 2 times 0 is 0. 0 squared is 0. That would be an instance because 0 does equal 0. I need to choose a number where this is not going to be true. So if you take a look at what x is and what's happening to it, they're showing you that 2 times most numbers is different than that number squared. All right, so let's pick something easy like I'll do 10. You'll notice that they chose 5 on the answer key. Perfectly fine as well. So I'm going to plug in 2 times 10. And here I'm going to have 10 squared. So 2 times 10 is 20. And 10 squared is 10 times 10. And that is 100. Not true. And again, that's a counterexample where up here this was an instance. Okay, so an instance is when it's true, and a counterexample, choose a number to show when it's false. And then the last part here, we talked about terms and what those look like. Terms can be a single number, they can be a single variable, or they can be ones that are combined through multiplication. Terms are always separated by addition or subtraction. So the number of terms here is 2. 4ab is a term and 25 is a term. PQR is just one big multiplication problem, right? That actually represents a number. If you knew what these were, you'd multiply them and that's a number. This is one term. This has 1, 2, 3 terms. And so to answer the question, which one of these examples is 3 terms, that would be the answer. And this one, 3x, that is 1 term. Okay, going to 1, 3. So looking at equivalent expressions, we are going to test these two expressions out and see if they are equivalent or the same. And so we're going to choose the same numbers. These ones are given to us, but if you had to do this on your own, you would pick the numbers that you want and try it out for both of them and see if similar inputs are producing similar outputs. Okay, so the first one I will write out completely. The rest I'm not going to. Just want you to see what's going on here. So I'm plugging in 1 for n to see if this expression equals this expression. So n becomes a 1, so it's 1 plus 1 plus 3 plus, and then inside here 1 plus 1. So this is 2 and this is 2, 1 plus 1. So it's 2 plus 3 plus 2, that's 7. And then over here on the other side, this is just 5 plus 2n, 2 times n, so I put 1. 2 times 1 is 2, so 5 plus 2 equals 7. So far, these match. Now, one single instance of this working does not prove that these are likely equivalent. We need multiple. Okay, so we're going to continue down this. So we're going to go 2 plus 1 is 3, plus 3 is 6. And then over here, I have 2 plus 1 is 3, right? And so when I add 6 plus 3, that's going to give me 9. And over here, 2 times 2 is 4, plus 5 is 9. So this works. I'll write this one out just so we can see it. 3 is now being substituted in for n. So these are both 4s because it's 3 plus 1. So 4 plus 3 is 10 plus, right, this is 4. 4 plus, 4 plus 3 is not 10. 4 plus 3 is 7. That's why I was confusing myself there. 4 plus 3 is 7, plus another 4 is 11. And then as we slide over here, this is 5 plus 2 times 3. 2 times 3 is 6, plus 5 is 11. So it's starting to look like this is going to work. You would run the rest of the numbers here. 10 plus 1 is 11, plus 3 is 14, plus another 11, that's 25. 2 times 10, that's 20, plus 5, it's 25. All right, and you can see these are going to be equivalent. They will be equal. I'm going to finish this one out. It's a little easier. 2 times 20, that's 40, plus 5 is 45. 35 times 2, that's 70, plus 5 is 75. And you would need to run these out. They do end up being the same. We do get 45 and 75, so these all match. Okay, so we filled this out. And now we can answer the question, are these expressions equivalent? And you would say, yes, they appear to be. Now we don't know for sure, but we've done enough work to assume. It says explain, so we do need to give a good reason. And here's what we're looking to say. Similar inputs produce similar outputs. Okay, last section here on the front. Got 1.4. So it says use the graph on the right to answer the following questions. And so if you look at this graph first before we start answering the questions, we've got these points. You notice they are not connected. And so that's all we have. The only information are these 4 points. So is this graph continuous or discrete? So a continuous graph is connected, okay, and a discrete graph is what we're looking at right here. And it says explain how you know. And so we are going to say it is discrete. That's the symbol for because. So it's discrete because the points are not connected. All right, next. What is the value when the function, what is the value of the function when x equals 0? So they can ask these two different ways, and we're going to see that here below. They can tell you what x is and ask you what's the value of the function. That's y. So they're looking for y. What is y when x equals 0? And then they can ask you what's x when the function, which is y, equals 4. Or what is the value of x when the function y equals that? And the way you keep that straight is they're giving you the x, right? And they're saying, what is x? So the other thing has to be y. So for this first question, what is the value of y when x equals 0? So find your x-axis and go to where x equals 0. When x is 0, this is the point we're looking at. At that point, x is still 0. Anywhere on the y-axis, the x value is 0, just the y value changes. Okay, and so the answer is 1. Y equals 1. You can write that y equals 1. You can also put the point 0, 1, perfectly acceptable. Either one is fine. So for the next one, what is the value of x when the function equals 4? So when y equals 4, what's x? So I come up to where y equals 4. We're talking about this. That's when x is 1. So when x equals 1. Or you can put the point, x is 1 and y is 4. Okay, what is the value of x when y equals 0? So now we're going to where y equals 0, which is here. That's on the x-axis. And that's when x equals -1. So they're asking you what is the value of x. We're looking for x given y equals 0. And so that point right there, the x is -1 and the y is 0. All right, to the back. Okay, for this first section right here, we're not going to worry about that here in semester 1, something we will go back to and cover later. So we're going to slide down to 1.6, absolute value and distance. So remember the basics of absolute value. If the number is positive, it stays positive. If the number is negative, it becomes positive. So both the absolute value of 5 and -5 is 5. What it's actually asking you is how far is the number from 0? That's what absolute value says. But the basics of it is it takes whatever's inside and it makes it positive. Now, if there's an operation on the inside, for instance, -4 plus 2, and you're looking for that answer, you have to do what's inside there first. Some people would want to just say, oh, that just becomes a +4 and 4 plus 2 is 6. That would be incorrect. All right, you have to actually do the math in here first, and then when you're down and simplified to one single number, then you apply absolute value at that point. So we're going to leave the absolute value alone. -4 plus 2 is -2. And now you take the absolute value, we're down to one number, and that becomes +2. So notice if I did it up here, I would have got 6, which is incorrect. Okay, so if there is an operation to do inside parentheses, you're going to take care of that first. Now, let's jump in. Find all the values of the variable that satisfy the equation below. So what possible numbers could be plugged in here to make this 5? We already touched on this. X could be 5, but it also could be -5. If I plug in -5 and take the absolute value, I get +5. All right, so most of the time these have two answers. Now, this one is not going to have two answers because we're looking at it equal to 0. Because 0 doesn't have a positivity or negativity attached to it, the only way to get 0 is to get 0 right on the dot. So the only way I can get A 0 here is if this was 5, because 5 minus 5 is 0. Absolute value of 0, it's just 0. And that's the only way to get there. There's no other number I can plug in for W that when I minus 5, I get 0. So the only answer here is 5. And then there is the option that there is no value, okay? No solution, because whatever number we plug in there, when we take the absolute value, it has to become positive. There is no way to get a negative answer after you've taken the absolute value. All right, next section. We're going to evaluate each one of these expressions. So what this is what it looks like in a lot of calculators. It's the absolute value. That's how they express it. They don't use these symbols. So we'll just translate these into the symbols we're used to, but we need to recognize that that's what this is saying. Absolute value of negative 10 plus the absolute value of 2. This is the absolute value of 5 minus the absolute value of negative 10. This is the absolute value of 12 minus 20. All right, so let's run through these. This now is down to a single number inside the absolute value. It's going to become positive 10. Absolute value of positive 2 is just 2. And so my final answer here is 12. Over here, absolute value of 5 is 5. Bring down the minus. Absolute value of negative 10 is positive 10. 5 minus 10 is negative 5. All right, and now this is one of those examples where we actually have to do the work first. We can't just make this positive. So 12 minus 20 is negative 8, still inside the absolute value. And now we take the absolute value of negative 8, and that's positive 8. All right, down to the last section, data and spread. We looked at mean, median, mode, range. We looked at different graphs. And would we consider them uniform, symmetric, skewed right or skewed left? And then mean, absolute, deviation. Those are the long ones. We'll get into that one in a second. First, let's make sure that we can label these. Uniform is unchanging. So the only one, everyone understands that this is skewed right and skewed left. You might mix those up, which one's which, but you understand if it's kind of going one way or the other, that's skewed right or left. But then we have uniform and symmetric. So uniform means all the same. If everybody wears a uniform to school, it means all the same. This is changing. This is all the same. So this is uniform. That is a graph that is uniform. And when it's centered, symmetry means it's the same on both sides of a line. It's like a mirror image. Okay, so this is a symmetric graph. And then these always mess me up because to me, this looks like skewed left. Everything looks like it's bumping over to the left, and this looks like skewed to the right. But when we actually label these, we're looking at what's called the tail. So this bump is a little bit to the left, and it's got kind of like two tails, right? This little tail here and this bigger tail here. We're always looking at the bigger tail, and that tells you if it's skewed left or right. So in this case, the longer tail is to the right. This is skewed right. And here you've got two tails. Longer tail is on the left, and this is skewed left. All right, we're going to calculate the mean absolute deviation. Last thing we got to do here. So remember what this tells you is how far your data is away in general from the average. We talked about when we covered this section, you could have two students that have the same test average, like an 85, but one of them always gets like an 84 and an 86 and an 85, and then another one gets like 100 and then a 60 and then a 95 and then an 82, and they're all over the place. So this is a measure of consistency because sometimes the mean or the average doesn't tell the full story. All right, so the first step for this is to find the mean. All right, and that is when you add them all up and divide by how many you've got. So I'm going to add all of these up in my calculator. You don't need to watch me punch all that in, but I do this plus this plus this plus this plus this all the way across, and that comes out to 630. And then I divide that by how many I've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so my average here is 63. Now, that's define the mean. It's no big deal. Step 2, you subtract the mean from the data. This is kind of the annoying part. So we want to know each piece of data, how far away is it from the average or from the mean? We express all of these as positives. Biggest mistake you see is that people express these as negatives because they just subtract, and depending on which direction you subtract, you might get a negative. We're not interested in that. We're looking at distance. So like 62 is 1 away from 63, and 64 is 1 away from 63. Those would both be expressed as just 1. Okay, so 61, I'll write this over here. 61 minus 63 is negative 2, but we're just going to call this positive 2. And that just comes from 61 is 2 away from here. So 64 minus 63 is 1 away. 63 matches it, so that's a 0. 58 minus 63 is 5 away. Yes, we would get negative 5, but we're expressing as a positive. We just want to know how far is it. 5. 62 is 1 away. 57 is 6 away. 61 is 2 away. 66 is 3 away. 68 is 5 away. And 70 is 7 away. So yes, you probably want to show all your work for each one of these, the little subtraction problems. But as you get better at this, something that kind of is annoying and takes a long time to do, we can find ways to do it faster. All right, so then you're going to add all these up. I'm just going to take it right off the key. If I add all of these numbers up here, I get 32. And you now average that out. So you're basically taking the mean of the new data. So 32 divided by 10 is 3.2, and that is the mean absolute deviation. So if we had another set of data, let's say that these were test scores, and another person's average was also 63, they could have a different mean absolute deviation. Again, let's say that they were more all over the place. They got a 40 on the first one, and then an 85, and then a 50, and then a 78. Their mean absolute deviation would be bigger, okay, because they, on average, are farther away from their mean from test to test, where this person on average, so we're just averaging all of these numbers that represent how far off of the average is each individual test score or each piece of data. On average, this person, or whatever this is talking about, is 3.2 away from 63. So it's a measure of consistency. We could compare it to another mean absolute deviation and say which one is more consistent.